So welcome to the seminar. I want to try to solve some problems that last week we discussed. One of the things about continuous we are arguing about for the eigenvalues. I think we should understand that the eigenvalues is continuous in the sense that we can take um, from an interval, so it's not discrete, and it can be the interval or whole real lines because we are dealing with the combination operator, so every eigenvalues is real. Or we also call it as the set of the eigenvalue is uncountable. So continuous in that sense is that meaning. So yeah, that's it from the problem. Do you have reference just from network? Okay. Last time I asked ChatGPT about this question. Yeah, so I cannot find it. Understand that ChatGPT it makes sense to me because later on we are doing the inner product for, let's say for because I am looking at the integral. So if I didn't change the notation yet. So if the C here is and taking the interval, so the interval will is make sense. You're still talking about yeah. Because later on we're dealing with the function, so and taking that D as the variable of the function of, let's say, function. But you haven't solved the Oh, that's a shame. For sunset is not this way. That's a mathematically we can how we can construct like like living in what space.
Just interval. Just some interval. Just means
then from removing from discrete to you use the analogy from you replace a discrete sum to the integral, and yeah, in the sense that we can write the autonomity convenience relation and cap inner product in the integral form. Last time we have we introduced about infinitesimal translation operator, and I associate it with I introduced the operator should be in this form. So perhaps I should mention about how this form is related to the initial one that I introduced in question 1.3. So I will continue from here. And we're taking the inner product between two cat. So this is a where this one is a function of x prime minus ds prime, where we will discuss this in details later. This one is actually what we are talking about, the wave function, and we expand the function because the function there's some fulfilling some constraints. We can expand it in the Taylor series. So Taylor series is an expansion about the x prime here, and big O here is the terms that containing and also including the x prime square. So with the first order approximation in the sense that we throw away all the terms that including and higher order than 2. So we have the infinitesimal translation operator having a form of 1.1 and 1.10. So how we can get the 1.10? So when we have been seeing about 1.11 here. So basically I'm comparing when I adding the operator t on a cat. So this one will be adding on the cat here. So by comparing this t dx cat x prime with this one. This will give because this is a number, so I'm comparing these two with this one. In a sense that I can write it as the 1.11, and yeah, comparing 1.11 with the 1.9 here, so it's like it's a wave function of x prime function of s prime minus ds prime. and pull out the side into the outside, and I get a translation operator as 1.10. Okay. I try to write out myself. Let's see. What is the meaning?
You just replace with the okay, so 1 point. What's the relation between 1.9?
It's a relation between 1.9 and 1.10. I'm using 1.11. This one is the 对面。And this one is equal to so I pulling up the if I'm writing on the and pulling out the this bracket here, and I get 1.10. It's like an operator adding on the bracket as point of. Does it yes? Then 1.11 is my tools to get the 1.10.
It's different, right? So you still like mix everything together, so it's very hard to mix. And supposingly they are equal through the first, but you put the you seems to imply that the last two are equal.
The last two, it means that my order is like the last two will come first before the first one.
And both of them should relate to the only then that two are the same.
The last two come first, then
So I mean that the last two equal to the first. Both of them equal
I use first and third one to get the second one. Oh,
Say one, one, two,
okay. Can you repeat again?
there are three terms there, right?
Mm.
Second and third. But why the second and the third? You repeat one.
What I understand is 1, 2, 3. No, what I understand that your center is 2, 3 is the same as the first. And they are equal. The first one are equal.
Follow what you say. Just know what did you say?
Or only then the second one is equal.
Then second one equal.
Equal to 3.
Yeah. Just 2 equal to 1, 3 equal to 1, so 2 equal.
Maybe the order I should change. So following the first step that we introduced before, so we encode the K operator with the Nabra here. And the I here we introduce in the translation operator so that we can.
In that case, you also don't need phi also, right? Don't need.
You mean I straight away write bracket?
The most important thing here is just there's another way to write down all the operator. Nothing special about phi here yet.
Or
Nothing special about it. Even if I don't know it is a wave function. The problem is you can press this
side five.
operator using the action of this operator using.
So I straight away replace it with a bracket.
Just write what you write here. Just write what you written down here.
Right, I what?
Written down.
I already write.
You written down.
I already write.
Write the blue thing, right? Isn't it you write one?
Oh, so you.
Yeah, that's what I meant.
Okay, okay. Okay. Yeah, the I we introduce here to satisfy the properties that we impose in the previous week. So and K here, K operator with a component of X, Y, and Z is the omission operator. And now we'll move on to derive some relation between the K operator and the X operator. First we adding the translation operator, then followed by the X position operator in specific. So the translation operator will do the job is translate the localized state into another translated state and measuring the position of prime plus ds prime. And another one, we interchange the operations and adding on the cap, x prime cap. So this one is a bit confusing. So the x operator adding on the operator here is this is meant by the eigenvalues we can pull up to the outside of the actions, and the translation operator will translate the state. As we subtract two of them together, and we use the Taylor series of expansion again to ignore the terms that is including the second order in dx. So if we do the Taylor expansions on the cat S prime plus ds prime, so and multiply with the outside of the ds prime. So the first order expansions multiply with the outside of the ds prime, so will be the second order, and we ignore the second order and the higher terms. Second orders and higher. And we arrive at commutation relation between the X operator and the translation, infinitesimal translation operator as follows. So we should understand that this is the, when we adding, this one is not the operators. So, or if you want to think it as the operator is multiplied with the identity operator, giving the eigenvalues of the S prime. Again, if we write out, we substitute the K operator. Sorry, we substitute the T operator with the full form in terms of K operator, which we can get a question 1.17, and there's some typo in between the 1.17 and 1.8. We're choosing the direction ds prime in the direction of SJJ can be 1, 2, 3. And dot product with xi on both sides. This x with the head is means by the basis. So on the both sides of the equation, we can obtain the translate commutation relation between xi and kj. So here we will ask what is the meaning of the K operator here. Here we will briefly go through about maybe just some sentence about the classical mechanics. From the classical mechanics, the momentum is the generator of the infinitesimal translation in the sense that we have canonical transformations. Canonical transformation is transformations that including the change in coordinates. That preserves the form of Hamilton equations. Hamilton equation is the Hamilton equations. There's the conjugate momenta and also the generalized coordinate. Preserve these two equations, the Hamilton equations. So why is it important to preserve the Hamilton equation? Because it will give us the dynamics of the system. It tells us how the system will be evolved. So, for example, if I change the coordinates, which is a kind of the transformations, I should expect that the dynamics won't change. So this is about the canonical transformations, and there is a type of the canonical transformations. If we change the x, change the original x here to the new x by adding the infinitesimal translation with dx. So this one is like we changing the x on x with the big X and big B. So the momentum here we didn't change it. So yeah, this is one type of the canonical transformations, and this type of the transformation can get from the generating function that is specifying these transformations. And I didn't include the details of S prime P. Basically, the X, if the generating functions is equal to S dot P. This one is the identity transformation, which is it do nothing on the coordinates, original coordinates. So if we compare the classical mechanics generating function above with our infinitesimal translation operator, the t here with 1 minus I k dot dx. The infinitesimal translation operator, if we look at the first term, if this one is equal to 1, when we adding on a cat, say on the cat x with the position x. So if we adding the 1 to the cat, is do nothing. So this is a similar form of the identity transformation in the classical mechanics. Identity transformation in the classical mechanics. So comparing dx and dx here, and this is a similar form which is related to the classical mechanics. So we are guessing that this k is the momentum operator in quantum mechanics. This is one of the way to get the how do we get the momentum operator. Another way to get a momentum operator is I didn't include here, which we intuitively think that a wave equations having the form of exponent I h bar p minus something. So how we can get the momentum in the exponent terms? One of the way we can obtain it is we should apply the partial derivative on the exponent to get down the exponent, to get down the terms in the exponent. So this is another way that introduce how we can get the momentum operator. So this one is like we compare whereas this k operator is the momentum operator, and we do the dimensional analysis on the k operator. So it has the length, it has the dimension of 1 over length because because x here, dx here is the length, so multiply together with it must be dimensionless. So we are guessing that the k operator and the p operator has the must be relating with the constant because the k here is not, the dimension of k is not equal to the dimension of p. And this constant here is turned out to be the h bar that appears in the de Broglie relations. De Broglie relations that introduce that have the metal wave that is introducing the h bar. So for it to be dimension equivalence. Why not? Oh, over h bar. I mean, yeah, the same. Yeah, I know to show that this one is creating the p over constant k.
Yeah, I know. The constant is h bar, right?
Yeah.
So why not just?
Okay. I mean, maybe a bit. I mean, not too much low. Yeah, also. I mean, low also.
Redundant?
Yeah. Yeah, so the t here, so the k here is a p over h bar. And if we substitute back into the translation operator, infinitesimal translation operator, will have a form of 1 minus I P dot dx over h bar. P here is the momentum operator. And that's how we get the combination relation between x and k. So we substitute again, the k become the p over h bar, and we will get a combination relations is between the momentum operators and also the position operators. Bring the IH bar delta ij. So here we also say that this one is the canonical combination relations, which implies these two are not incompatible. No, these two are incompatible observables, and hence will give us the position momentum uncertainty relation. So we'll move on to the how we can represent the position operator in the position space and also the momentum space. And just now we also found that the momentum operator is the kind of form in 1.22, how we can get the exact form in position space and we'll move momentum space, and how this momentum space and position space can be related to each other. So let's say we have a physical set. We start with physical state alpha, and can be expanded in terms of the eigencats of the position observables. So this one is the include the identity operator here. Again, I want to emphasize the base cats or the eigencats of the position observables satisfying these eigenvalue equations when we adding the operator x on a cat with the eigenvalue s prime, we'll get the eigenvalue equations. And also normalize in the sense that if we're taking the inner product between two eigencats, it will satisfying autonormality conditions. So indeed, the wave mechanics, the language that using in the wave mechanics, the wave functions is actually is in the sense that we can express when we taking the inner product between the physical state with the position eigencats. So this is the wave function in the position space, in the sense that it's a function of x prime. And sometimes we also call it as the wave function in position representations. So if we note that the 1.24, if we do the some analogy to the discrete case that the summation of when we want to express the cat a physical state in the linear superpositions of some basis. So this one we can see the wave function here. It's like the expansion coefficient that we defined earlier. So, and again, we want to interpret it as the statistical ways, so known as a form statistical interpretations. So we're taking the expansions coefficients for the wave function here. We interpret it as the probability for the particles to be found in the intervals of ds prime around x prime. Again, if you see the inner product between the two physical states, so what is how we can write in the wave function language? So we're taking the inner product between two physical states and using the combined relations of the second cap of position operator, impose it in between the beta and alpha. So we'll have the form of this, in the sense that this one, we taking the conjugate on the inner conjugate on this inner product. So we'll interchange with S prime and beta and get the wave function, get a function form by beta. So because we will ask like this one, if it's specific in the position eigencase. So indeed the representation is not fixed, and we'll see how we can represent it in those other spaces. This one will suppose a state alpha. The state alpha that can be expanded using the eigencase of the operator A. So the operator A has the discrete eigencase, discrete eigenvalues. If you multiply the both sides and taking in the sense and taking the inner product with the eigenbra x prime here on the left. So here this one will give us a wave function, and this is the expansion coefficient, and this one we express as the eigenfunctions. We call it as an eigenfunction of operator A, which we will give the eigenvalues of AI in the position basis. Why we call it as an eigenfunction? In the sense that if we adding the operator on the eigenfunction here, it's like in this spaces, continuous spaces is the defined as this ways, and the A operator adding on the cap give the eigenvalue, and this is exactly the eigenfunctions. So in the sense that if we say that this is an eigenfunction because it gives us operator adding on a function given an eigenvalue and functions. And now we'll examine how this inner product, the A operator adding on the a physical state and taking inner product with another physical state can be expressed in the terms of the wave function. So again, if we impose the covariance relations in between these two, then we will get the similar form of the matrix entries that we introduced a few weeks before. So in the sense that if you want to know what is the inner product, we need to know that what is inside here. So in general, this is the in a continuous basis here. So this is a function of the two variables S prime and also S double prime. So let's say we want to do it as the best we can see it in the general form. So let's say we have the operator is a function of the position operator, and there's a f of x, and f of x, and x here is the operator that's akin to acting on the cap. So say we have the inner product is, and this when we adding the observer A, which is a function of the position operator. So we will get the eigenvalues of S prime here. So it's a function of get a function of the eigenvalues, and taking the inner product between the eigencats is the using the autonomity conditions. Generally, if we substitute it equation 1.3, in general, if we substitute it into the equation 1.33 here, like substitute the observer A, which is a function of position operator in the equation 1.33. We should get a is in this form. Again, here we use the Dirac delta functions here, which is the autonomity conditions to get the final form of equations. So here what we achieve is we express the inner product between the A acting on the alpha physical state with the another beta physical state expressed in the wave functions language. So in the sense that when we want to adding the operator A on the wave functions, so we squish in between the two wave functions. We are squishing inside in between the two wave functions. Here we will see how we can get the momentum operator in the position space. So we start with just now we have the definition of the momentum as the generator of infinitesimal translations. So in the sense that with the T here, we I bar H. So here we expressing in the one dimensions. So one dimension stuff. So when we adding this translation infinitesimal translation operator on the physical state cat. So if you and express is in the position eigenbasis. So the translation operator acting on the cat will give us a translation of delta S prime. And again, we change the variables from the S prime. We change the variable to S prime to equal to S prime plus delta S prime. So we have the equations of 1.35. And here is the terms that is at the end is a function of x prime minus delta S prime. It's a function of these functions. So we're using the Taylor series, Taylor expansions around the delta S prime, around delta S prime again. And again, we ignore the second order, like we did a few slides before. So the second order terms with and also the higher order terms will discard it. And we replace the 1.3, we replace the 1.35, the terms inside 1.35 with the 1.36. We discard it. And we compare both sides of the equations. After substitute into equation 1.35, we will get the momentum operators. We get the momentum operators is expressing in between the as this form. And if we taking the inner product with the eigenbra here, taking the inner product with the eigenbra here, so in the sense that this one in inner product with and we'll get the form of the momentum operator in this form negative I h bar del over del s prime. And in the now we will express the P in the position basis. The position basis, the P in the position basis here, for the matrix element of P. So in a sense that we obtain the values. In a sense that if we taking the P operator, adding on the X double prime, and inner product with the X prime here. This one will, this is exactly the IH bar del X prime as the equation 1.38, and also inner product with the X prime and X double prime. So this is the autonomy conditions that we are using. And for the two states, if we have the two states of physical state alpha and beta, from the equation 1.37 here, 1.37. We're taking the inner product of between P adding on alpha cat inner product with the beta. So we can get equations of this form. Again, in the sense that if we adding the operator P in between the two physical states, it's like squeeze the operator inside the wave functions. And here we conclude that the momentum operator in the position representation is in having the form of P equal to negative I h bar del over del X prime. So this one is for the position basis, momentum operator in the momentum basis. How about the momentum? Operators and also wave functions in the momentum basis here? Suppose we have the momentum eigencats that is spanning the cat space, where the basis cat or the eigencats is satisfying the eigenvalue equations when we adding the operator P or the cat P prime. We have the eigenvalues of P prime. And it forces that it satisfies the autonomy conditions in the sense that the inner product between two cats satisfy the Dirac delta functions. Again, if we starting with the arbitrary physical state and we expand it, we expand the physical state in the momentum basis. So the momentum basis here is the continuous, we have the continuous eigenvalues. So we expand it in a fraction of 1.43. So this is similar to the cat. If we expand the cat in the position basis that we found, that we saw it before. So here again, we see that there is the expansion coefficient here, and we interpret these expansion coefficients here as the momentum space of wave functions, in the sense that we can write as the phi of physical state alpha with taking the values of interval values of momentum. So this one we interpret as the probability of measurement of P, which will give us the eigenvalues of P prime within the interval of D P prime is this one. And also we want the physical state to be normalized in the sense that taking the inner product with itself is equal to 1. P prime is the interval. dp prime is the integral with interval, this one dp prime.
Within an interval dp.
Can
you read the sentence?
Sorry.
Yeah.
No. Yeah. dp prime we find similar interval.
dp prime is an interval.
Yeah.
So what does it mean by a number times density?
In the 1.4.
The dp prime is that number times dp. What does it mean by interval times number?
Interval times number. This one we interpret as probability density. It's a density, right? So yeah. Time interval of let's say length. So will give us a probability.
Like interval 0 to 1.
What exactly the length?
Yeah, so so I'm asking you, so what's the number?
0 to taking the.
So you multiply by number. So multiply by 2 is what? I need to see.
I should get it as this one as the number, which come from an interval.
But that's not you. You're trying to say, right? You say within
an interval. Or maybe I should say that the interval in between, we can find a probability of, we can have the probability finding this particle of giving the eigenvalue.
no. Do you see your sentence of problem? There's no problem. What's that interval? Can you write down the interval? Right.
Let's say 0 and dp prime.
Let's say or always like that. It's always. So dp prime is your endpoint. This interval. The dp prime is a number or is an interval? Simple question.
Number.
It's number, right?
Yeah.
So number is not interval, right? So is it okay to write like that? You think?
I think that that's
Still no problem. Number and interval the same or not? I ask you.
yeah, it's different, but
It's different, okay. So why
I
should you write?
understand the probability of finding that of
I
having
don't
that
care about probability now.
it's in that
I don't
interval.
care about probability. I'm asking you what's the interval?
Yeah, it's in that interval.
What
So
interval? Okay, right now.
like 0 dp prime.
It's always like that.
Is it always like that?
Is the only interval you
Not only not necessarily to be, but that is the length will be dp prime.
length will be dp. That's not what you meant. What do you mean by interval? You want to say interval with a length dp prime?
Interval of the length. Okay, interval of the length.
Do you see the
Yeah.
difference or not?
Just straight away link.
I don't care how you link up. Do you see the problem or not?
Yeah. So interval with a length of dp.
Then that makes sense. Number times number in the end.
Oh. Yeah. So yeah, this one is also the same as the own interpretations, own statistical interpretations, and yeah, so nice. So just now we have two forms of two spaces. The sense that we have, if we represent the wave function in the with the positions basis, so we call it that wave functions is in the position space. If it's in the momentum basis, so it will be the momentum space. So I want to build a connection between these two basis of representations. So yeah, for example, if you're looking for S representation to the P representations, and the information should be contained in the inner product between the
Wait, something wrong here. The English. What do you mean by
looking for from
here? Looking for a transformation or
looking for a transformation from S representation to
where looking for transformation? You are not looking. You need to look.
Of transformation. From S presentation to so the transformation functions is encoded in the product between the eigencats of P prime and S prime. So if you want to derive these transformation functions, and we call back with the equation 1.38, having the put side by side. Yeah, we're replacing the alpha here with the p prime. Decided adding the p operators, momentum operator on the eigencats have the eigenvalues of p prime, and taking this is the things that we want to have the transformation functions, and this one is the momentum operator, the form of momentum operator that we found negative I h bar del x prime that we said before. If and the differential equations, if we taking this is if we solve for the s prime integral s prime p prime, solve for the this differential equations is in the form of exponent ip prime s prime over h bar. And here n is the normalization constants. We will determine it later. So this will be the transformation function that we want as a function of two variables s prime and p prime. And when we solving the differential equation here, we fix the p prime here, and yeah, I get a solution for this differential equation as well. The time form. So to solve for the n here, the normalization constant here, to normalize we consider the inner product between the two position eigencats s prime and s double prime, and we expand it in the momentum basis. The left hand side is just the from the autonomity conditions is just Dirac delta functions, and the right hand side we can substitute the solution that we found before 1.46. That says that we have the this exponent, and to arrive at the last line here, we use the Fourier transform. The Fourier transform from, in general, we have a Dirac delta transform from the exponent, the Fourier transform from here, taking the Fourier transform. So the n here is we're taking the n to be real and also the positive by the conventions. We arrive the n is the form of 1 over square root 2 pi h bar. And now we are ready to transform between the position space wave function and also the momentum space wave functions. So, for example, if we have the wave functions in expressions in for example, we have a wave function that is expressing in the terms in the position basis or in position space. This one is more in momentum space. If you want to transform the wave function in the position space, in the sense that we are taking this expression to transform the wave function in one space to another space. Let's say if we from the position space to the momentum space, Gaussian space to the momentum space, taking impose the equations into the form, in this form. So actually this pair of equations, these equations and also this pair of equations is exactly similar, is similar to the Fourier transform. So apparently that if we have a wave function in one space or in another space, the Fourier transform will tell us how to transform them between two spaces. Okay, suppose we have the position operator is adding on the cat, and adding on the cat and impose the cat and impose the combination relations in between these two. So adding the cat, sorry, when the operator adding on the cat will give us the eigenvalue of s prime. So eigenvalues of s prime, and we have the equations here. And we multiply both sides with the eigenbars, adding the eigenbars on both sides. So the eigenbar will, because these are eigenvalues, and we adding the eigenbars with the cat here. So is this one is eigenfunctions in the variables of it's a wave function in the variables of x prime, and also this one, the p prime s prime here is the transformation functions that we found in 1.49. This here is 1.49. And if we treating this, how we can get the s prime from the exponent, how we can get down here. So we can think of like we taking the differentiation with respect, partial derivative with respect to p prime here, respect to p prime on the exponent. So we're getting down the negative I h bar negative I h bar x prime. So and we cancel out with the I h bar at the outside. This one and this one is the wave functions that is expressing in the momentum space. Y s prime is the partial derivative. Like this one, if we adding on inside of the exponent, so we'll get s prime down. So it's like a reverse working. Reverse engineering. These two are the same, right? No, it's not equal part. We adding the operation, get down the s prime. Eigenvalues.
So why we need
To get the eigenvalue that's in exponent terms go down. And I mean
why eigenvalue?
value inside. why I doing this?
Why X prime is in there over there?
Because when we adding the del over del, we prime inside, adding on the right hand side, so right side here, the S prime will go down. And I mean S prime negative I S prime over by H go down. I mean taking the
Understand that? Why X prime?
S prime is not equal.
If I equal, then why you can say
In the expression is same.
go to the X prime of it. X prime of
Do the S.
X prime of the S.
If we seeing at the second last line to the
You write down prime of that. Calculate the new thing.
in S prime on the exponential. One is
Yeah, same question. So I ask you why equal.
not equal.
By definition or what? Is it by definition?
By the operations of a partial derivative. I think on this is exactly
When we S prime by definition is the
no.
we know. No, then why are they equal?
It's not equal because this one is outside. That's why it's inside. The other one is inside. Outside.
What outside inside?
X prime inside. The other one outside. Why these two are not equal?
I don't know. I ask you why they are equal. I didn't say they are not equal. Sorry, I didn't say they are not equal. I just asking you why are they equal. I didn't say they are not equal. I didn't say.
Why?
I'm just asking you why are they equal.
Because of the operation of the other one.
So that's why I asked you. I know what's the operation.
Partial derivative.
Huh?
Partial derivative.
No, I already tell you I know it. I just asked you why these two things are different. Do you recognize they are different or not? One is S prime, one is del over del B. Do you recognize they are different? The different symbol by first of all. Different symbol. Why are they the same?
They are not the same.
I didn't say they are not the same. I asked you why are they the same? I didn't say they are not the same.
Why are they the same of you mean the equations?
Why you write equal sign? Very simple, but why then you write equal? Why you write equal?
But this is
That one I know, but that one different.
I mean reverse way to get down. It is obvious. This one is obvious. But if we reverse,
Get the reverse. How to reverse? You mean that last line is equal to
last line is equal to
this? Sorry. So the second line of the right equal to the first line on the left. Is that what you mean?
this is obvious to you, right? Why this is not?
I don't know what is S prime now. I don't know what is S prime. What is S prime? S prime is an operator, isn't it?
This one is just a reverse way.
So I can't see. S prime is a number or operator?
It's a constant. If we respect to P prime,
S prime is a constant, the eigenvalue.
eigenvalue constant.
S prime is an eigenvalue.
Eigenvalue constant. Constant with respect to P prime.
Then shouldn't you put H bar over I instead of IH?
One over I is
cancel out the I.
yeah, one over I is negative I.
F bar is the eigenvalue.
It's eigenvalue. Yeah. Yeah. Yeah, this one is the if we seeing this x is a operator, x1 is eigenvalues. If we seeing this x operators adding is the position operator is in.
So I think you really need to change it.
Yeah. I haven't changed it.
You also
Yeah.
Not sure why they pick this.
Yeah, the position operators is in the momentum space. So the position operator in the position space is just an operator adding eigencat, getting the eigenvalue as prime and also eigencat. But in the momentum space is will be adding adding the IH bar del P prime on the wave functions. This one is the position operator in the momentum space. So actually, this will be the first half that I want to present. So, and the second part, question that you bring out is not make sense to you because these two can be cancelled out. I'm not sure if aware of this. F here is the function we taking the function as the input and we output as the values. And hence the functional derivative here is like the dy dx here that we cannot cancel with the dx. So why cannot be cancelled in specific form? I mean, in specific, in rigorous way, I don't know why is it. And yeah, so the point that I want to bring out, I mean, and if we move forward, I want to bring out is these iterations is the total change in f with respect to the change of the function phi. So it's like we have a functional. So let's say it depends on the function on a function x. no, fx. So fx can be changing. So if we thinking it in the xy plane, so the function, I mean, can be changing. So we want to measure the total change of functional in if the function is changing. So in the sense that the total change here is due to the variation of function phi. So the total change in f is the linear superposition of the local change at certain points. So in that sense, this functional derivative is actually function. So I think this one is quite not make sense for me actually. So if the delta of a functional over a delta of a functions, it becomes a functions. When the derivative becomes functions. And if this one is a function at a certain point, so the total change we just take sum over the total over possible points. So will be a total change. And every integral. Can I just use this to express the proof first?
Exchange, phi change. If phi change, then f will change.
Phi change, yeah, f will change.
So it's a function.
Function of x. You take
X change. Phi will change. Phi change.
f will change. In the questions. Oh, okay. Okay. This is the before we move on to Lagrangian, which is using the functional. So, and the variation of the phi here, we're taking it as the Dirac delta functions. In the sense that this have a strength of epsilon. The Dirac delta function have the properties like if you take in the integral the delta functions and the function of x. So, and if you give a result of f of y. So, and with these constructions, we substitute the Dirac delta functions as with epsilon as the delta phi, and we arrive at the functional derivative is the limit. And so another big terms that understand is like generalized functions, distributions. The other function is generalized functions. To see the properties of derivative, functional derivative. terms here, what exactly it means. Yeah, this one's I think this part no need information. For classical mechanics, we are dealing with the point masses in the sense that we have describing by the discrete set of the coordinates. Usually we call it as a generalized coordinates in Qi. So before we go to the quantum field theory, it's supposed to think to review about the classical field theory. The classical field theory that when we treating the discrete set of the coordinates to be the continuous. Continuous in the sense that yeah, it's not discrete. It's now the generalized coordinate will be the continuous field variables. Usually we denote it as the phi here. So and now we will using the Lagrangians and Hamiltonian principles to derive the dynamics of a field. So the Lagrangian functions, previously in the classical mechanics, it depends on the q prime generalized coordinate and also dot q prime. We treat these two as the independent variables, although in the sense that, in our sense like the positions, if this one is the usually it's the positions and this dot q prime is the velocity. The first thing that shouldn't do these two will be equal, but then in Lagrangian we start with the point.
You don't mean by equal, right? You mean that dependent.
Yeah, dependent. And then we start with a point that we treat these two as independent variables. So yeah, independent variables, and we derive using the Hamiltonian principle, and we after that we will see that actually is dependent to each other. Okay, so yeah, we treating these two variables as the dependent variables. So this one we are using the square bracket here, so to express this is depends on the function phi and also function of dot in dot phi, time derivative of continuous field variables. But it didn't depends on the x itself, so it depends on all the point. So we'll follow a path of the classical mechanics to find the equation of a motion of a system. So we want to apply the Hamilton principle of least action of the Lagrangian. Hamilton principle of least action is taking the variation of x. Variation on the labile. Now we're using labile. Variation on labile is equal to 0. In the sense of we are finding the extremum of the extremum of labile. So yeah, this extremum will describe the dynamics of a system. This is from the classical mechanics. So we want to apply in the generalize into the classical field theory. So now the variations of the function L, if we using the 2.1, we found it for the variation of function F. We can express as these two, in the sense that I understand it as these are two variables. So we're taking the taking it as total differentiations. Okay. So if we want to see the action W. The action W here is also a functional of function that depends on phi and so phi dot. In the sense that the action here is taking when you have the two fixed point T1, T2, taking the integral over the Lagrangian. So we're taking a variation of W is same as taking a variation of this integral. W is so. And we have a L just now. We move the delta inside the L. So delta, I mean, move inside, so we will become a delta L. Delta L is the equations that we use that we found 2.7. And we perform the integration by parts. Integration by parts in the sense that these second terms can be expressed of like, is it obvious to you? If not obvious, then I should. The second, this one, we perform the integration by part of second term, we'll get a result of this and the boundary conditions is equal to 0. Try to write. In the sense we pull out, we can interchange the del over del t and also the, I mean, partial derivative with respect to t and also the delta here, because what I understand is delta is acting on the functions, relation of functions, and the partial derivative is on the variable t. So we can interchange these two operations. Yeah, sorry. I mean, yeah, I see. So, yeah, it's here. So I just now talk about the then linear operators and delta acting on a function, partial over partial t. Partial is acting on a coordinate, so hence they are commute. I understand. And the Hamilton principle of Lake's actions that is describing the dynamics of a system is when the variation of a W is equal to 0. Apply it and we'll give us the equation of this 2.9 is equal to 0 in the sense if we looking back the equations here.
So we're taking equal to 0 by applying the principle of regression. This one, because it's a variation of phi, it not necessarily to be 0 everywhere. So for the function, I mean for the integral to be vanished, the inside should be vanished that intervals T1, T2. So and as we get the result generalization of Euler-Lagrange equation to the field theories. And noted here we are using delta over delta, so it's like the variations. It's still the variations. It's not the normal partial derivative of differentiation that we are like to see in the normal way. Because I don't understand. About this one, Euler-Lagrange equations. This one is for the Lagrangian that have the Q and Q prime as the Q and Q dot as the variables. So this one is, so the 2.9 is the generalization of 2.10 to the field theory. And to change it to the partial derivative, we introduce a Lagrangian density. The Lagrangian density, we also consider local field theories. Local field theory in the sense that the Lagrangian density at certain point x don't have the additional dependence on the value of the field at other space points, like y. Let me rephrase this. It means that the Lagrangian density didn't depend on 2 points of the 2 space points. So yeah, this is a local field theory. The Lagrangian, in the sense that the Lagrangian density can be written as the integral over, and it can be written as the Lagrangian can be written as the Lagrangian density integral over the volume. And the Lagrangian density is a function using the bracket, not a square bracket. So it depends on the function phi and also the space derivative phi and also time derivative phi. And we're taking the variations again, taking variations on the Lagrangian. In the sense that we're taking variations, so it's taking a variation on the Lagrangian density. I'm not sure this one how to link to the partial derivative if you're taking the variation on Lagrangian density. Because what I understand is the Lagrangian is a function, so function depends on this phi. It's a function, so we change it to the partial derivative. Again, also the partial derivative, and we multiply the variation of the function phi dot, and also nabla phi. Gradient. It's a gradient. One delta L delta.
Because now you got delta is this for
Delta. This delta. X. We continue. This again, the second one we use the Quadraro again.
integration by parts again, get the result. Second term here. You can pull out the delta by outside. Yeah, we use here. So set here. It vanish at the boundary terms also. So we compare and yeah, we arrive. So we are using this to arrive the last line 2.2. We compare 2.12 with 2.7. 2.7 is this one here. SL is here. So we compare this with the 2.12. And we found that the expressive expression for the functional derivative and functional derivative, as we mentioned, it should be a function. So, and we successful to express the functional derivative in a function in terms of functions. So this will be using this to A and B to find to use in afterwards. So we substitute into the Euler-Lagrange equation for the field theory 2.9. This one 0.9, and we get the Euler-Lagrange equations in terms of functions field theory. And if you want to express in the relativistic notations, can be and taking the C equal to 1. So this one is will tell us how the dynamics look like in the field theory for the classical field theory. And this one, the field equations, the form of this. And this one is at most at the equation of motions. If we derive from the Euler-Lagrange equations here, the equation of motion will be at most at the second order. So which is quite fit. Which is sufficient for us. For example, if we have the Euler equations in the first order, both sides is in the first order, and also the prime order equations is the second order on both sides. So when we have a Euler-Lagrange equations here, so which is quite sufficient for us. And classical mechanics. In classical mechanics, we have the canonical conjugate momentum. Canonically conjugate momentum. So in the same way, we analog to the classical mechanics, we define the canonical conjugate field by the functional derivative. So the P replaced with the pi and with the functional derivative here. So again, the functional derivative we mentioned is it should be a function. It should be an ordinary functions. So it's a defined point-wise, I define the continuous field variables. And using the Euler-Lagrange equations for 2.9 again. 9. You get you can express the time derivative of the pi canonical conjugate field in the form of the functional derivative. Again, we'll start with just now we have the Euler-Lagrange equation to describe the dynamics of a system. So following from the classical mechanics, we want to have the Hamilton formalisms. Hamilton formalisms in the sense that just now the Lagrangians is in one of the coordinate is, for example, is phi, another coordinates, independent coordinates is phi dot. So the Hamilton formalisms kind of like want to express the independent variables in the same order, same order, same order that is not like it's not like a dot Q. So and it's kind of the region. It's a form of it is a legendary transformations. Legendary transformations that you're changing in the sense that you're changing the variables um, to its conjugate. So the Hamiltonian here is the transformation, legendary transformations. Change a variable from again we taking the Hamiltonian one taking the Hamilton density defined as HT terms of these four variables. So the conjugate field and also the field variables and also their space derivative. And 2.21 is the 2.21 is the variation of variation of h, which is depends on the phi and also the pi functions. Again, is have some few slide. Okay. Okay. The variations of the sorry, we stop at 2.21. Okay. And again, we substitute. No, we're taking the variation on the legendary transformations that we define in 2.19, taking the variations. In that sense, it's like the product rule. Del pi, also del phi dot, and also negative del L. And it's equal to this because of we are using 2.7, 2.17, and 2.18. It's quite. And we compare the two equations as 2.11 and also 2.12. The 2.11, the variation on hash, and also 2.12, we start with taking variation on the legendary transformations, and we express it in another form. So we have the phi dot, the time derivative of a few variables in the functional derivative, and also the time derivative of the conjugate few variables in another functional derivative. And again, here we taking a variation on the Hamilton density, which is depends on the four variables. Again, it's just the total variables. Sorry, it's just the differentiation depends on these four variables. And again, use the integration by parts on 2 times, and which is vanished at the boundary, and we arrive at the time derivative of the few variables and also the conjugate few variables in expressed in the function derivative of functions, and we shall make use of the Hamilton formalism and also Lagrangian formalism in the field theory to apply it in our Dirac equation and also the Crandall equations, which in that sense we are treating that Dirac equation as the field and also the Crandall equation as a field. Yeah. The next step, will be we're seeing that prime quantum field is for spin zero particles, Dirac field is for spin half particles.
And this one, we are following the canonical quantizations. Another quantization ways is the how to do quantizations. So just now we have the convention field, we have the field variables, we promote it into the operators. So that step will be we jump into the quantum field theory. Yeah, and I will end here. Thank you. Photo.
正确放置。下则